We can see slides.
Okay, fine. So I'll start. So thanks for coming to this talk. I'm Enzo Crance, and I will present our article, Compositional Preprocessing for Automated Reasoning in Dependent Type Theory. So you all know that how crucial automation is to develop complex formal proofs. In proof assistance, we can build elaborate proofs with inductive types, dependent types, etc. So we have many different tactics for proof automation in the Coq proof assistant. So in those tactics, we can have some with very precise theories, such as LIA or ring. We have some more general tactics targeting SMT theories, like the SMT Coq project or the iToto project. And we also have proof search tactics, which are internal to Coq, like Crush, SOTO, or First Order. And we have even more general tactics based on context analysis, like Hammer. So this is great. We have various tactics to help us in a lot of situations. So we can see them in action. Here's an example of goal, which is provable by Hammer. It successfully combines lemmas about length, reverse, and concat. But on this goal, if we bring a slight modification, the goal then fails because of arithmetic. So we can try another tactic, handling arithmetic, like an SMT tactic. Let's take the one from SMT Coq. It can successfully prove this arithmetic goal, but such tactics can fail because of the input domain. For example, if we change the X quantifier for a type int from the mathcomp library, then it's not in the standard library and the tactic fails. We can try an even more specific tactic, like LIA. It can identify more arithmetic types, so it works on this goal. But in day-to-day proofs, we have other theories involved, such as the theory of equality. And by design, LIA will fail on this uninterpreted function because it was specifically made for arithmetic. So we can choose to jump back to a more complex tool built on LIA to benefit from its features. So let's take the SMT tactic from the iToto project. It will work on this goal, but we can run into trouble with Boolean logic with iToto. So what can we say? All these tactics target specific theories and their specific associated implementations, and that might hinder their use in Coq. So if you are well versed in the implementation details, you may know the reasons of failures, and in particular, you may know that these are not bugs. But in general, we cannot afford to expect the working Coq user to know all this information. So to ease the use of automation tactics in Coq, we propose a compositional preprocessing toolbox, which is a set of preprocessing tactics. By compositional, I mean that some are useful and some are not according to the context. The order of application of the transformations can change. And here we want to tackle the general problem, not to specifically target an automation tool. So we have two categories of transformations that we might want to build. The ones that go from the dependent type theory we have in proof assistance to first order logic. So this requires going from higher order functions and dependent types to first order logic, which is in general well handled by ATPs. And the second category of transformations is the ones that try to make sure the versatility of the specification language in the proof assistant does not block automation. So here are our contributions. We have built a collection of general small-scale and compositional preprocessing tactics. By general, I mean agnostic with respect to the backend. Small-scale means that each tactic is a specific transformation, and by compositional, I mean the flexibility I was talking about in the last slide. So to showcase our contributions, we can take an example. If you have ever tried to formalize the language with binders, you might have run into trouble proving properties related to the Brown indices. So we'll take an example, as example, the development by Sakaguchi. It's a formalization of lambda calculus. So we take an inductive type representing terms. We also take a fixed point shift representing the shift operation, where you shift by d positions the variables above threshold c in the term t. And we'll take two examples of goals, which describe some properties we might want to prove about shift. And here we can see that the orchestration tactic we have implemented, which is called snipe, successfully proves both of these goals. The induction remains manual because the goal contains an inductive type, and this needs to be manual, but the automation can kill all the other sub-goals. So we can see these goals contains inductives, fixed points, arithmetic, especially with natural numbers, and we even have logic in bool and prop, and Snipe is able to prove them. So I will present the pre-processing tactics. We have three kinds of them, the ones for inductive types, the ones for handling symbols, and the ones targeting first order. So let's talk about inductive types. For inductive types, the objective is to interpret them and interpret inductive predicates as well. So we can do an inversion on inductive predicates. We can expose properties of algebraic data types, make them explicit in the context. And some of these properties can contain existential quantifiers, and in some cases we want to get rid of them. And we can also eliminate pattern matching. And I will present three of these transformations. So for inductive relations, let's take an example. Here is an inductive relation relating two numbers to their sum. If we have add nmk in the context, we want to explain what add means at first order. So the transformation creates a hypothesis H prime explaining the content of the inductive relation. For algebraic data types, we want to interpret the list data type on this example. Our transformation generates several hypotheses. So first, the non-confusion property, stating that a list cannot be made from two different constructors. We have injectivity of all the constructors. And finally, we have the generation statements stating that the list must be created from one of the constructors. About pattern matching, match is a high-level construct, so our transformation is able to decompose it into two different hypotheses, and in the final proof context, there is no match anymore. So now let's talk about symbols after talking about inductives. By symbols, I mean uninterpreted constants. So we want to go from an uninterpreted symbol in the context to a context with a lot more information for ATPs. So in Coq, we can unfold constants. When they are defined with fixed points, we can manipulate the equations to get other ones easier to handle. And we can also perform some theory-based pre-processing, which is the transformation I'm going to present right now. So let's see how this plugin called Tract works. We'll take a theory, arithmetic, and a tactic suited for it. So we'll take LIA and an arithmetic goal. So on this goal, LIA is okay and can prove it. But in Coq, we have a lot of flexibility, and we can build a range of subtle variations over this goal. For example, we can choose to encode the integers with another type. So it's another implementation of integers. It's okay with LIA thanks to the Zedify preprocessing tactic, which is specifically tailored for LIA. Now, if we take another implementation on the type int in the mathcomp library, it's not in the standard library anymore. So Zedify could not preprocess it, but there's another layer above ZDFI called MCZDFI, which allows to prove this goal successfully. Now, a detail about this goal is that nowadays formalized maths don't only use parsing to overload notations, but they also use type class mechanisms or type class-based mechanisms. So the %R scope here means that the multiplication and addition operators are both desugared to type class operators. So here you can see that the preprocessing starts to be tricky, but MCZDFI is okay with that. Now, if we take a goal with a user-defined type, a theory of equality, type class-based notations, and Boolean equality, we're starting to put too much for LIA, so the automation of this tactic is no longer available. And as the preprocessing built for LIA was specific to this tactic, it's no longer available. So Tract was basically born from this need. So let's inspect this goal and see what's hidden behind the notations. Here we can see that equality is actually a type class operator as well. And it's the same for multiplication and addition. They all take a structure about the int type, and it's not the same. So each is a different type class. We need to recognize that they all amount to functions over int, even if it's not obvious at a first sight for the tactic. So here we take a tactic tract in the plugin, which takes two arguments, one for the target type for the theory, so here it will be Z, and another one for the logical target, which is a bool in our case. So the tactic will try to express all the values in Z if their initial type can be embedded into it. And as the initial goal is in Boolean logic, we will remain in bool in the end. So here you can see the output goal, and it's the same with all values in Z. And in particular, you can see that the type class-based operators have been changed for more direct implementations over Z. So unlike other transformations presented before, Tract uses a knowledge database filled by the user. So we have commands to register equivalencies between types, between relations, and between symbols. So here you can see an example about equality and addition. And we have an additional command to handle genericity. So let's take a diagram to sum up how the tool works. So we can see the Tract plugin. Here we have the knowledge base. First, we will fill the knowledge base with the commands. Then we will take an initial goal G and some parameters, as I saw, Z and bool in the example. The tool will use the knowledge base to produce an associated goal G prime, as well as a proof that G prime implies G. Then we can run an automation backend of our choice, or further preprocessing in the case of an orchestration containing Tract. And then with the proof of G prime, we can combine it with the other one to get a proof of G. Okay, so this is the end of the presentation for symbols. Now, for first order, the objective is to align the proof context with the scope of an external prover. So, for example, we can monomorphize the hypothesis in the context, or do a pointwise version of higher order equalities. And all the transformations are detailed in the article. Now I will talk about orchestration. Okay, so the snipe orchestration tactic. If we take our coq goal and the context, we can apply transformation in various ways on this goal and context, and the combination of the tactics is called scope. And then, if we run a backend, so SMT-coq in our case, we get the snipe preprocessing tactic, which is the one who is able to kill the goals shown in the examples. So now let's see the examples. Let's see the transformations in action with the example from the beginning. So we will take our term inductive and the shift fixed point. If we take an example of goal, so this is the one stating that shifting by 0 is an identity. With the induction and snipe, we can kill this goal, and let's see what happens on the context. We need to interpret in the sub-goals the term inductive type and the shift fixed point. So what happens on term? The no confusion hypotheses are the following. For each of the constructor, we have injectivity as well, and we have the generation lemma. About the shift fixed point, we can have a definition unfolding first. So a new hypothesis is generated. Then we can choose to eliminate the higher order equality by adding the arguments. So this is another transformation doing that. Then we can remove the fixed point. Then split the pattern matching into 3 different hypotheses. Each one talking about one constructor. Then as you can see, there was an if construct, which is in reality a matched construct, so we can further split it into 2 new parts, H9A and H9B. And now let's take the H9A, and we'll talk about the track transformation on it, because it contains an inductive type and natural numbers. Here we can see the H9A hypothesis after preprocessing, and you can see that all the arithmetic is expressed on Z, especially the comparison operator and the addition. So in conclusion, what can we say? We have a collection of compositional transformations, which are standalone. They can run on their own, but we can combine them as well. And as they are compositional, you can add your own. Here I want to stress that feedback is welcome, because we can test our tool and help you use it. So if you want to send us some code, it's welcome. The compositionality allowed us to use several meta languages in the process. So we used LTAC, Metacoq, and CoqLP for various tactics. And we have built an orchestration in the Sniper plugin, which is called Snipe. And again, this one is also one example, but you can choose to make your own, and you are free to make another orchestration if you want. So thank you for your attention, and feel free to install the tools and give some feedback, and we'll be happy to help you.
Thank you for the presentation, Enzo, and there are some questions.
This is really cool work. I'm wondering if the pre-processing steps you do can be incrementalized, so that as you learn new hypotheses or something like that, you don't have to resaturate the whole context every time.
Sorry, I didn't hear the question.
Can you hear me?
Yeah, better.
Okay. So I'm wondering if the saturation phase that you're running, the pre-processing, can be incrementalized, so that each time you learn a new hypothesis, you don't have to resaturate hypotheses that may have already existed the last time you ran the pre-processing phase.
Okay, so I think the orchestration is made so that the saturation happens after generating the required hypothesis. So we probably don't have to come back to it. But I don't know if Chantal Keller is here as well, but I actually developed the track transformation, and so on the orchestration, I'm not really the most knowledgeable person in the group. So I don't know if you need more details, maybe she can give.
Hello, can you hear me?
You have to speak up a bit. We don't hear you.
Is it better? Is it better?
It's not really better. No.
I'm trying to get closer to my laptop.
The closer you get, the better. I think.
Okay. Hello. So yes, about your question. For the moment, we have to really separate everything all the time in this first prototype. But of course, we would like to do some caching and to first, and also to be able to be more incremental as you suggest, but it's not implemented yet.
Thank you. All right. So let's thank